I might just sit down so that I can plug the microphone, so that you can all hear a bit more easily. Just at the back, is that pretty easy to hear? Yeah, good. All right, so first I'll just go over who's here today from Wargaming. So Richard and I, we're going to be doing the presenting. We're both software engineers, and we've been working at Wargaming for about 6 years. We've also got Isabel from our HR department, and we have Kira, who recently graduated from the University of New South Wales, and now she's in Wargaming Sydney's internship program. So just to provide a bit more background for the speakers, Richard and I've worked in the games industry for over 10 years. Before Wargaming, I worked on facial animation and capture technology for LA Noire, amongst other things. Richard's worked previously in film and visual effects, including for the Lego movie. And at Wargaming Sydney, we're both on the same team, and our team has primarily been focused on core engine work with a performance focus and computer graphics work. So some of the things that we've worked on at Wargaming include include adding DirectX 11 support to World of Tanks on PC, some core engine multi-threading work for World of Tanks to help it support multiple cores more effectively. PlayStation 4 core technology work for World of Warships Legends, which was launched on PlayStation 4 and Xbox One earlier this year, and just a lot of other graphics and porting work for other titles. So today we're going to talk. There's three main sections to this workshop. So firstly, we're just going to give this introduction, a bit of context on the games industry, and just some things about how games are produced, and some of the things that are involved, and some background on Wargaming Sydney, what is Wargaming, the company, and our internship program. Then Richard's going to talk about engineering and game development, engineering and how we work on these large-scale productions. And then I'll talk again about writing fast code, something that's quite important for the types of games that Wargaming produces. Alright, so what is Wargaming? So I looked it up on Wikipedia, and we've got over 4,000 employees and 20 offices. It's a big international company anyway, so Wargaming makes AAA high production value titles so there's a lot of complicated technology behind them, and gameplay that's kept millions of active users engaged. So World of Tanks and World of Warships are amongst the biggest massively multiplayer titles in the world. And Wargaming has a huge company that has a lot of games. So there's World of Tanks, World of Warships, World of Warplanes. They're on PC, console, mobile, most of these, taken online. This is World of Warships Legends. Like I mentioned, this launched earlier in the year, and this was something that we worked on our team, contributing to the technology behind that. This is World of Warplanes. And this is Wargaming's largest title. This is World of Tanks running on PC. This is all rendered using the game engine. You can go and download this for now for free, as long as your PC is powerful enough. This is what it looks like. So you can see these are pretty complex, cutting-edge pieces of software. All right, so I'll just mention some things about Wargaming Sydney specifically. So Wargaming Sydney previously was Big World Technology, and they were creators of game engine middleware. It was a game engine aimed at massively multiplayer online titles. It provided all the server code needed for the games, as well as the actual game 3D engine and so on. This technology was used to make World of Tanks, and when that exploded in popularity, Wargaming, one of the acquisitions they made was to acquire Big World Technology, which became Wargaming Sydney. This server and client technology still underpins World of Tanks PC, World of Warships, World of Warplanes, and the server technology is used more widely than that as well. So when Richard talks, he's going to give a bit more of a description about what actually is a game engine. The Sydney office has generally been a technology centre, providing technical solutions and working alongside the game teams. Like I mentioned, we worked on the PlayStation 4 underlying technology for World of Warships Legends. The primary development team was located in St. Petersburg in Russia. Recently, the studio's been building up headcount in other areas, such as art and game design, so that we can cater for a wider variety of projects. You can see here that there's quite a few people in the studio that generally we work in team sizes of maybe 5 to 10, so there's a lot of smaller projects in progress at once. So there's work in network programming, machine learning projects, graphics, physics, rapid gameplay prototyping, virtual reality, augmented reality. These are all things that we've worked on, and it's something that sort of keeps the work fresh, I think, the variety of projects. Alright, so I just want to try and give a very high-level overview of the games industry and some of the considerations involved and the development process. It's only going to be 5 or 10 minutes, so that hopefully it gives you a bit of context on what we're sort of working on. So games are basically just complex software projects. So but there are a few things that are maybe they're not completely unique to games, but they're at least unusual, and they're challenges that you might not face in writing some other software. So one of those is that they're a creative thing. So there are sort of two parts to that. It means that it's a multidiscipline collaboration. So I'll talk soon about all the different disciplines that are involved. You know, there's art, there's game design, and so on. There's obviously engineering, and it can be complicated to make sure everyone's needs are being met at once, that everyone's communicating well, and that everything is running efficiently. Anyway, I find it's a little easier, maybe, if you're working on a pure engineering project and you don't have to take into account collaboration across all the different disciplines. And part of it being a creative project is also that it's hard to define what is fun. Like software projects are hard enough to come up with a design and implement it, and then it all works and you're done. But once you add in the creative element as well, it makes things even harder. Like, how can you can't really, it's very hard. Maybe if you're a genius game designer, you can just know this will definitely be fun, we'll make this and it'll be successful. But that's pretty unrealistic. It tends to be an iterative and unpredictable process, and part of the process for making games is about trying to minimize risks related to that. At least for the types of games that Wargaming makes, like big high production titles, performance is a critical aspect. So good performance makes a huge difference to the user and the quality of their experience and how competitive it is with other games. So it's not unique to games, but it's definitely something. It's more, performance is much more important than in a lot of other industries. And part of that relates to one of the other things that for games is the platforms that we have to run on. So some other industries where performance is really critical, like financial trading and so on, or say back-end services at a big company like Google, they control all of their hardware. If they need things to go faster, they can pay for better hardware. They don't have, like, whereas for games, we can't tell all of our users to upgrade their hardware. We can't tell Microsoft to make the Xbox go faster. It's fixed hardware. We have to get the best result we possibly can if we want to be competitive with other people who are already doing that on each of those systems. And when it comes to PC games as well, there's a lot of sort of engineering effort in making sure we deal with variations in hardware, variations in performance, and compatibility issues running across, say, Like World of Tanks only just recently dropped Windows XP support. And you might think Windows XP, that I imagine you were all born when Windows XP came out at least, but it's pretty old. And it was difficult to keep it well supported. Yeah, it's definitely something that other projects with more control will have to deal with. And just a bit of a mention about business models for games, because that's even a bit different to a lot of other software projects as well. It's more like film or whatever for a lot of cases where you just buy a packaged game. It's very hit-based, so there's a few games that make a lot of money and a lot of games that don't make much. Maybe they don't even cover their costs, which is similar to films, and publishers sort of. This is one of the reasons why you see so many sequels, because if you can have a fairly sure bet, then you're pretty likely to make a sequel. But publishers also try to make a lot of games to sort of reduce their risk, because if one of them is a hit, they'll pay for everything. But as well as that, such games make almost all of their money pretty soon after release. Like the game comes out, makes all its money, goes to the bargain bin, and then it's off the shelves, and then you better hope that you're working on your next release, because that's where you're going to generate more business. It is changing over the last sort of decade or so. Like all of Wargaming's games, basically, massively multiplayer online, and they're not like this. They release and then they're continually developed. New features are continually coming out, and that way there's generally a longer tail of it. But anyway, it's just something to consider for engineering. If you're engineering for something to be released once, support it for a small while, then move on to the next thing. It's different to if you're thinking we're going to support this for 10 years. Right, so just again, very high level overview of the development process. It's obviously not exactly the same everywhere, and it can depend a lot on the team size and those sorts of things, but generally you would go through a process like this, where first you start off with pre-production. It's basically a planning sort of a phase, so you would be trying to answer maybe business questions, like what's the budget, what's the timeline, who are we making this game for, but also you're wanting to mitigate a lot of the technical risks, the creative risks, like what art style are we going to use, like what are we actually making. A term you often hear used at Wargaming is finding the fun. So you want to make sure, you don't want to put a huge team on something for a year and then find out, this isn't really very fun. So pre-production could often involve doing prototypes, or like a vertical slice, it's called, like just a small segment of the game, and a lot of iteration just to make sure that you know what the core gameplay is, and you're confident this is going to be fun. This has a market of people that will want to play this, and so on. So after pre-production, you should know what you're going to make, what you're aiming for, and hopefully have a plan in place for how artists are going to work, and all those sorts of things, and probably documentation about like game design document and so on. So after that, you move into production. So that's where you actually make the code and all of the content. It's the main stage, and it's the expensive stage. So you may, after pre-production, decide we're not going to continue, we're not confident enough, that you want to hope that once you finish pre-production, you're confident enough to put all the money into it and maybe put a team of 100 or so people on it, rather than pre-production, which would probably be a much smaller group. And even no matter how much planning you do, it's likely to be an iterative, creative process still once you get to production, but you just want to avoid having to completely change the game because you find out it just doesn't work, or it's not fun, or no one wants to play it. And then the other phase that you would generally see is maintenance. And like I already mentioned before, that can differ dramatically depending on the type of game. So single player release, it might just be you release a few patches, or maybe you release a bit of DLC and then move on to your next title. But for something like World of Warcraft or other large games and Wargaming's free-to-play titles, maintenance can be the main phase, and it can go on for years and years. So just to give a bit of a quick example, like I guess just to pull something out of the air, like a Mario Kart clone. Say you thought, I've got a good idea as a company, we've got a Mario Kart clone, we've got a bit of a twist on the gameplay, we think this is going to be good. Pre-production will probably involve like, what art style are we going to use? Who are we going, finding out who are we going to target? How much is this going to cost? And testing, like, does this seem like something that's fun? Maybe with a prototype with like one rough track with just placeholder art or something like that. Once you're confident enough and you've got a plan for how you're going to actually make this game, and you've decided that this does have a market that is fun, then you'd move to production with a big team, and you'd have artists going through making all the tracks, game designers working through iterating on the details of the gameplay and so on, and engineers working on making the software actually work, and then you release it. And yeah, it's just a very high level overview, but hopefully that gives a bit of an indication of the general process. So, like I mentioned before, there are a lot of roles involved. So, just to give a bit of a quick overview, there's art, obviously to create all the content. There's concept design, like defining, say, what is the art style that we're aiming for. Like the art lead and so on need to be able to. Artists working on creating the content need to know what style are they using, what do things need to look like. There can be lighting artists, 2D artists, 3D artists. There's a lot of different sub-disciplines there, but basically they decide what they want the game to look like and to create the content. There's design, so that's game designers, like deciding on the gameplay, the rules, the structure of the sort of game process. QA, so they're basically responsible for testing that the game doesn't have defects. That could also be part of defining this process for quality control, and it could also be subjective feedback if they're doing daily play tests, like is it feeling fun, what's working, what's not, and so on. Production, there's a lot of different roles involved there. It can be internal to the studio, or it can be external in the publisher who's financing the game, but generally they'd could be working on tasks like managing the development team, reporting on progress, scheduling, hiring, budgets, and so on. And then there's obviously engineering, which we'll talk about later. And it's interesting to note also, I think there's bridging roles. So there's technical artists that know a lot about the technology and also about creating the art and the tools that the artists are using and so on, just to try and make sure that, in some cases anyway, that engineering and graphics engineers are working well with the artists, that they're understanding, everyone's understanding what everyone wants, and so on. Alright, so Richard will talk more about these different sort of sub-disciplines for software engineering and games when he talks, but basically the engineers drive what's technically possible. They help clarify these sorts of things with designers and artists. Like an artist might come and ask a graphics engineer, can we do this? What can be possible? How could we achieve what we want to do? And they get everything to work. So another big part is that they can amplify the productivity of content creators. On a big production, engineers can be outnumbered substantially by artists and game designers and so on. So work that they can do to make it so that the process of generating content is smooth and reliable, and make it so they can concentrate on making things look good or play well rather than fighting with tools. Yeah, it can make a big difference to the final result. Alright, so just want to mention a bit about the internship program at Wargaming. So there are 2 intakes per year with 4 months full-time each. So the next one is expected to be in March, and that would be advertising in January and expecting to do interviews in February. It's generally aimed at graduates or students skipping a semester to get industry experience. One thing that we're aware of is that UNSW has switched over to trimesters, so this, yeah, we're sort of thinking about what we can do to make this better for UNSW students, but right now I think this is the intention for the next internship intake at least, and yeah, it might be, if you want to know more about the internship program, it'd definitely be worth talking to Isabel from our HR department, or Kira, who's currently doing the internship program after the presentations. Okay, so for internship applications for engineering, or for just general applications in general for any level of role, there are a few things that I'll mention that are good to be able to see on resumes and that sort of thing. So something that I like to see, like sometimes we have applications and there's no interest in game development. There doesn't seem to be much of an interest in games, and you know, they could still be a good software engineer, but a good software engineer plus someone who can talk about games and they can talk about games technology, like I would view that more positively. So just being able to talk about it, having an enthusiasm for the technology and so on. If you've even worked on some projects, or some of your university projects have been in technology that's applicable to games, it'd be great to be able to talk about those sorts of things with someone in an interview. C++ that's another thing that's positive to see. So Richard will talk a bit more about languages in his presentation, but C++ is something that's still quite desirable for the games industry, especially for AAA big production titles. So anyway, if someone has C++ and can talk about C++, that's something that would also be viewed favourably. And just probably the most important thing is in general just being able to talk about problems that you've solved, projects that you've worked on, even if they're university projects, or it could be other things you've worked on outside of university. Because when you're actually working, you will have problems you need to solve, you need to be able to think of solutions, talk to other people on the team about it, and so on. And so it's confidence inspiring from an interviewer's perspective to be able to see, oh yeah, you work through these problems, you can talk to me about the details, even if it's just to say, I done this and it didn't work very well, it was bad, and here's what I would change next time. And there's plenty of other things, like if you've used Unreal or Unity game engine, you've done some graphics work, performance profiling, optimization work, networking, user interfaces, just anything that would apply to game development. And the last thing I'll mention in this introduction is the Sydney Game Developers Meetup, which could be a good way to learn more about games development if you're interested. So it's a monthly meetup at Wargaming Sydney. There's presentations on a lot of different topics, all of them are game development related. It generally starts around 5:45 p.m. in the Wargaming Sydney office, and hopefully this link is clear enough to read. If you searched in Google for Sydney Game Developers Meetup, you'd find it if you're interested. And this link has all the details of upcoming presentations and where to go and what time. One thing I forgot to mention at the start is if anyone has any questions, just put your arm up and we can answer. Otherwise, just come to us afterwards, and there's plenty of time. That's it for the introduction. So now I'll let Richard talk about engineering and game development.
Hello. Can everyone hear me? Sorry. So my name is Richard, and I'm here to discuss the engineering approach that we have in our production environment, mostly from the perspective of working at Wargaming Sydney. So while doing my bachelor degree in computer science here at UNSW, I graduated 15 years ago, so I started earlier than that. Started in the year 2000. It was a long time. But I remember graduating and not having very much of a perspective of what a production level software development role would actually look like. I didn't have a clue what the environment that I would be working in, the tools that I would be using, and I didn't have a really good appreciation of the extent to which understanding the hardware, the computer that we're actually running on, understanding that hardware actually makes you a better software engineer. So I'm hoping that this presentation, between my slides and Scott's next slides on performance, actually give you a better perspective of this. So I'll be discussing engineering from a few perspectives, both technical and non-technical. And I understand that the technical side of things will probably be more appealing to you and the degree. I think it's really appropriate that we do discuss more of the soft skills of a software engineer, as they're often overlooked or underappreciated, and I think they're really important. I think it's crucial to keep all of these aspects in mind when you consider your own employability or your ability to thrive in this profession for a long period of time. I asked around at the beginning when people were walking in, can I get a quick show of hands who's in first year uni? It's just, I don't want to make anyone feel uncomfortable. Second year? Cool. Third year? Or more? Third year or more? First grad, PhD, at least. Okay, and computer science, or is there a mix of computer science engineering? Computer science hands? Okay, engineering? No. Okay, so there's a good mix. It's nice to see a bit more of the sort of senior level students as well. Hopefully everyone will get something from these particular slides. So what is engineering? I quite like this definition from the Oxford Dictionary. Engineering is the action of working artfully to bring something about. And the thing I really enjoy about this particular definition is the implication of creativeness and mastery in our profession when we do something artfully. I think that it's something that we are all really striving for when we become software developers. And I really hope that we're all generally passionate about being software developers. We're passionate about being good software developers, and that we have a passion for the industry that we're working in. So the combination of all of those things is really ideal. But in the context of production software development environment, I don't want to discuss engineering in a bit more of a broader context. It's no longer solo or about you. So here are some of the technical and non-technical aspects I'd like to talk about. So I want you just to take a moment to consider what you know now about software development and put that at a much larger scale. An industry level production environment is a large machine, and there, like any large machine, there's lots of moving parts. It's a complex system and it requires coordination. In the software development environment, you have a lot of complex code that a lot of people are writing. You also have a pipeline, which is a transformation process that both your code or your game content. I worked in visual effects, so the pipeline there was a little bit more obvious. There were actual physical departments where a particular animation shot or film shot would transfer through. It would start off storyboarding, then will be laid out, modeled, animated, lit. The whole, you can see this is a pipeline of work. So that's a process. So you have code, you have a process, and you have lots of people. And in order to coordinate this effectively, you need lots of tools to help you do your work, and you also need tools to help the coordination. You're working in a very highly collaborative environment. Your team, as in our case, is actually international, and it's often many, many groups of people. So this leads to the need for tools that do things like issue tracking, wiki-like document systems. Is wiki even a thing now? Do you guys? Yeah, good. Version control systems, version control for your game code, your tools code, your resources. Build systems. Actually, maybe I'll start from the top again. I'm curious who's actually had any experience with any of these things. So has anyone used issue trackers before? Yeah, cool. So maybe I should start with version control. So version control is probably, I'm hoping, something that most people have been using. It's really easy to use version control now with the advent of GitHub. It sort of integrates the use of the version control into accessing software. And it also comes with issue trackers inside of it, so in GitHub or in GitLab. So have people used, what kind of version control systems have people used? You want to shout something out? So GitHub, the Git?
GitLab?
So yeah, okay, cool, Git still. Has anyone used Subversion? Has anyone heard of Subversion? Oh, wow. I am old. Probably not. Mercurial? Perforce? Heard this? CVS? Going back. Okay, so Git is like the primary version control system. Okay, cool. Certainly understanding version control systems is crucial to working at an industry level. It may not always be Git that you're using. In our case, it's not. But understanding the ideas or the paradigms associated with version control will help you to work in many other version control systems, or just at least to be able to move between them with some level of understanding. What about build systems? Oh, yeah, sorry?
Sorry, did you mention which version control are you using in Wargaming?
It's a mix. It's a mixture. So some places use Subversion, some studios. Perforce is something. No, is Perforce free?
I'm not sure. There was like a trial. Not many users.
Perforce may not be free, so and it's certainly something that I wasn't aware of before starting work at Wargaming.
It used to be free for like 2 users or something.
They're the primary two, and they're both not distributed version control systems. So they're centralized. There's a server serving the code to the many clients. It's a technicality that you may not care about. Okay, build systems. Are people aware of things like Jenkins or JetBrains' tool TeamCity? Things like this? No? Okay. So these are systems that you can set up that work in conjunction with your version control system to do things like automatically compile your code when you check it in, to run tests, to automate a whole bunch of really interesting, or sort of automate some of that process as part of your development environment. And they're also fairly crucial to the work that we do. And so at least having an understanding that these things exist is probably key. And we also write a lot of our own tools to manage production-specific complexities. So that's just kind of the gamut of tools, and there may be more, that you might be involved with when you move to an industry-level software development role. And they're all very valuable. So learning things like Git now or any other version control system, making it part of your daily software development. So if you're doing any hobby programming, just integrate that in, so start to learn how those kinds of things work, will make it easier to move into an industry role. And just remember that you are working with lots of people in an industry role. So it is important that you learn how to communicate your ideas and just generally talk with people. It's also important to learn how to accept and give feedback, both sort of positive feedback and improvement feedback, and ensuring that you're giving constructive feedback all the time. So we should all really be striving to become better professionals as you move into an industry role. Okay, now for something a bit more technical. What is a game engine? I've stated here that what I think a game engine is whatever is needed to run or make or run your game. So a game engine is just a set of libraries or tools that make up your game. And in that perspective, consider all aspects: the audio, the visual, your control input into the game itself, the networking components, content creation, game logic, etc. So there are many flavors of what a game engine actually is, and there's no right or wrong. It's what is right is whatever works for your game and the thing that you're trying to produce. It doesn't have to be a game. It can be whatever your software project is, you choose a design that is right for you. At Wargaming Sydney, we deal with quite a few different engines. As Scott mentioned, the big world technology licensed both server and client technology. So there are different flavors of the game engine that floated around with the server technology that we have to work with. There are also a couple of other in-house engines that Wargaming as a whole support, and that we also deal with at Wargaming Sydney. There are a few teams that have dealt with Unity and some teams that are dealing with Unreal now. So both off-the-shelf and sort of bespoke game engines are what we are dealing with at our studio. The game engine itself is classified by the capabilities and the architecture, its design. So just bear that in mind. It's like I said, it can look at engines come in very, very many different flavors, but you can consider them for the needs of your project. All right. So when I discuss software development roles later on, hopefully you'll get a clearer picture of the different parts of the game engine from a software development perspective. So, with regards to software development itself, you don't have infinite time. Your time is precious. So it's important that you ensure that you're spending your time appropriately. So software design becomes a series of trade-offs for this reason. So it's really important that you remain pragmatic when you're making decisions. So to remain highly productive within these constraints, it's really important to have really clear goals about what you're trying to produce. Clear goals help you decide what design choices you're going to make, and it helps you to prioritize what features or issues you actually are going to bother solving. When Scott was discussing the lifetime of a product, of a game, when you're dealing with the pre-production vertical slice, just trying to test out a gameplay feature, you're not really concerned about the intricacies of your game engine at that point. You really should be focusing on what you need to do just to get to the end and test whether that game feature is something that you want to keep around. So make sure that you have clear goals. The other part is making your development process really easy. And I want it more in the context of being able to iterate on changes, on your features and on your bug fixes really quickly. It is a highly iterative process. The quicker you can iterate, so the quicker your game can load, or the quicker your frames will run, the quicker anything, or the quicker your processes occur. So perhaps after content creation, your processes transform into something else that your game uses. Anything that can be sped up means that you can iterate on changes to those systems much quicker. So you can try new things, and you can increase the number of things that you're trying within the small amount of time that you have. From a quality point of view, make sure that you test, and where possible also automate those testers. So become familiar with how you can possibly automate these build systems that I mentioned previously, a continuous integration system, can do lots of these tests for you if you design that into your code. So allow your code to be testable, automate it, make sure that you're running the tests, and you'll reap the benefits without too much of your extra time, your cognitive time. Yep.
When you say make dev process easy, do you use tools like Slack or Trello? Have you heard of those?
We use Slack internally to communicate. The Wargaming uses a combination of communications tools. So communication is one aspect. We use Slack and Skype and whatever else. When I'm talking about making the development process easy, I suppose I'm more referring to how you design your code, how you create your code, should have in mind not just the game that the user is playing, but the fact that you'll be spending many years creating this, so making sure that your development process can be streamlined is also crucial. Does that make sense? Cool. And just a note on languages, as Scott has mentioned, I'll talk about what we use. So games are often performance critical bits of software, and at Wargaming as a whole, we mainly use C++ because it's a higher level language with some interesting features, some interesting additions to C, really. And so the combination of that gives us most of the control of the lower level hardware that we need it to run on. We need our games to run on. So learning C++ is fairly crucial within the games industry in general, I would say.
Yep. How would you say about like Java or other OOP languages? Where are they positioned in the game industry?
I am not aware of many other Java games besides Minecraft. Yeah, Minecraft might change it.
C#.
Yeah, so Unity and the engine use C# as their primary language. And there are some game studios moving over to Rust, which is not object-oriented as far as I'm aware, but it's a language that can at least compile down to something efficient.
I think that if you took away C# and C++, there wouldn't be many games.
Yeah, so primarily C# and C++. With Rust coming up the rear, it looks like it's making more of a running C++. So games are also a combination of this high-performing code and some kind of scripting language that we use to drive the high-performing code. So where performance isn't critical, or gameplay particularly is scripted. So at Wargaming Sydney, we mostly deal with Python as a scripting language. There's also Lua, which is used by one of their custom engines internally. But Lua you see around the traps too. LUA, if you're looking at it. So while C++ can produce fast code, the language definition itself is rather big, and it can be really confusing. So it's really important that when you learn a language like this, that you try to understand the nuances of the language itself. And know enough of the nuances that help you to skip lots of the common mistakes that lots of people would experience in using that language. And programming idioms for a particular language tend to cover these kinds of mistakes. So do a search online for C++ idioms or Python idioms, and you will see little phrases of code, how you might try to phrase a problem to not have lots of the mistakes, or to be the most efficient that you can be within that environment. And it's easy. So know the hardware you're running on is the next point to the language. It can be really easy to write naive and really poor performing code. And the language itself may not save you. C++ is a good case for this. So be aware of how your code is actually compiling down. You can use something like Compiler Explorer to see the assembly, or you can use your own compiler to view the assembly. So know how it's compiling down and know how that compiled code actually runs on the hardware that you're targeting. So Scott will talk more about this, but it's really, really crucial. Things like the language itself doesn't often give you a good indication that what you're about to do may perform poorly. Things like the use of, I hope you guys are aware of C++ to a degree. Yes? No? Hands up if you've used C++. Okay, so very few. Learn C++. So things like using the virtual keyword, or overusing the virtual keyword, or using new too much, so allocating on the heap too much, is something that can really destroy your performance if you're not careful. And if you're not careful, you need to use these things, but you need to be aware of the consequences. Again, Scott will discuss more about this. Also, get used to using a debugger. It's a fairly critical part of the role. It's a critical part of my role, anyways. So understand how to use something like, I don't know which environments you guys tend to be using, possibly Linux related, so GDB or LLDB. Get to know it. Maybe some of the GUI front ends would help assist your knowledge of this. Those tools are really, really powerful. We work in Windows, so we're Visual Studio development environment based, or Visual Studio toolset based. So Visual Studio has a reasonable debugger, as well as Windows comes with another one called WinDBG that give you some really handy insights and fairly decent control over your debugging environment and what you actually want to introspect from a running program. GDB has some really cool features, so get to learn some of those things. They're also quite customizable. So with GDB, I think you have Python. I imagine LLVMs, so LLDB, has a similar sort of scripting front end. So you can script your debugging as well, which is quite cool. In Visual Studio, you can write plugins to enhance your debugging experience. Right. So some of the software development roles. Okay, we're in a multidisciplinary environment. What does a software developer actually do? Scott had the list that I'm about to, so already presented the list.
Payloads, we're writing 20 bytes of data for every element. And the other thing is, this is how the linked list is laid out in memory. So this is a large part of the reason for the extra cost in filling the linked list. Every time we put in a new node, we have to do a memory allocation, and the cost of those really builds up. And the other thing is, those memory allocations can be all over the place, just wherever the memory allocator happens to position that next allocation on the heap. So when we're iterating over it, the effect that you're seeing here is that this is really inefficient for the CPU's memory subsystem. We don't only have to read 20 bytes per node, but the CPU, there's too much to go into detail here, but the CPU has a prefetcher, and so if you've got predictable memory access patterns, you can read ahead and know what you're going to need and put it into cache before you even need it. You can't do that with an access pattern like this, just going all over the place, and so on. But another example where knowing the low-level details can make a big difference is in C++, the standard set is like a red-black tree. It's a form of binary tree, and all the nodes are allocated like this, like a linked list. When you add a node, there's an allocation. There's extra pointers and things, and populating my test vector and then sorting it was 10 times faster than filling up a standard set with the same elements. And then in my sorted vector, doing a binary search was over 2 times faster than accessing an element from the map. So I just thought that was a reasonable example of knowing a bit about how the CPU works, knowing how these libraries are implemented can make a big difference. So in this first case, if you just thought, list that has the same scalability as vector. I'm going to use the list. You could have something 20 times slower than someone who thinks, I know how this is implemented, I know that the vector is going to use way less memory, it's going to be way more efficient for the CPU to process and so on. And this is just a bit of another example. So we've got a two-dimensional image. I don't know how much image processing work anyone has maybe done in their course, but basically the image data is just a big array of pixels. And so we've got all the color values for the first row, then all the color values for the next row, and so on, until we're finished storing all of the rows. And what we want to do here is do something like a blur of the image data. And that could be implemented as a pass going across all of the rows. So we would iterate, like do a for loop going over every single row, like all the pixels along this row, then all the pixels along the next row, and then a vertical pass. So we blur things out horizontally, then we blur them out vertically. So the next one would be iterating down the pixels of the row. So it'd access one pixel, then skip a long way to access the next one, then skip a long way to access the next one, just because of the way the data is laid out in memory. Does that seem clear? Hopefully I've described that clearly enough. So what sort of, does anyone sort of have any sort of feeling on which path, whether there might be any performance difference between these passes, and if so, how much difference might there be? Like, would you have a preference for going across this image data horizontally or vertically? Yeah?
Would it make sense to be more vertical, since like the monitors have to be rectangular, they have to have a longer length, but they have to be short on the vertical side, not on the side. Would it make sense to do vertically? Also, it also works I'm not sure if that makes sense, but I think it also makes sense for multi-monitor systems.
Well, I guess in this particular case, the most important thing to consider is how this is laid out in memory. Because for displaying it later, generally on any display, the data is in memory as scanned lines. You have all the pixels for one row, followed by all the pixels for the next row, followed by all the pixels for the next row. So the thing here to think about is how, and where there's the big impact here again, is how this works with the CPU's memory subsystem. So when we're going through the horizontal pass, where we have a very predictable access pattern, where we one pixel, then the next one, then the next one, and I guess a cache line I don't think is something that you would be familiar with, but when memory is accessed into the CPU's cache, it doesn't just grab the one byte that you want, that you're reading, or anything like that. On this laptop here, on most systems, it grabs 64 bytes at a time. So as we're going along, it'll grab 64 bytes. We'll go, it'll be very fast when we access the next pixels, because they're already in that 64 bytes. We've already fetched. The CPU's prefetch will start to think, you seem to be going this one, that one. I think you're going to keep doing that. So probably it'll just keep reading all that stuff in as fast as it can before you're even using it. When we start doing the vertical pass, we're reading one pixel, then we're skipping through our array all the way up until we get to the first pixel on the next line. Then we're skipping all the way up until we get to the first pixel on the next line. We're only using one pixel's worth of that data. So, and like I said before, we fetch a whole cache line each time, and the skips are too far for the prefetcher to be able to see any pattern. So on this, not on this machine, on the machine at work, this vertical pass is 9 times slower. Like this is quite, if you could make your CPU go 9 times faster, you'd be pretty happy. And just simple things like this can make a huge difference. So anyway, I just hope that was another good example of just how much, when you're designing software, you might, like, I know when I've designed blurs and so on, I would try to think, how can I structure this so that I will be going only horizontally, because, or and so on, or or otherwise restructure this so that the memory access will be efficient so that I can avoid this bad case. Because this was on a fast i7 with big cache as well. Like this could run a lot worse on a lesser system. Alright, so now I'll just try and quickly go over measurement. So measurement, and like a lot of this other stuff, it maybe just seems like common sense, but yeah, measuring performance is critical. If you don't measure performance, you don't know where time is being spent. If you don't measure performance after you've made changes that are performance targeted, you don't know what the impact of those changes were. And if you're not measuring it regularly, you won't know when there are regressions. So, and I guess part of the reason for stressing this is that it's not rare at all to see people optimizing something that wasn't the problem. Someone might just be like, oh, that'd be the problem, and then they fix it, and they're like, oh, that didn't make any difference because it wasn't the problem and they didn't measure. Or maybe they think they won't fix something in the area they're more familiar with, or something that was more interesting to change, or something like that. That if you don't measure and focus your changes, then measure afterwards, your efforts are likely to be misguided. And I thought there were some interesting examples from a talk that Microsoft gave at the Game Developers Conference of this exact thing. The Xbox Advanced Technology Group, you can go to them. They'll have some Xbox engineers sit with you, go through your game, and they can help you find performance issues and things like that to help your game run better on Xbox. And some of the things they've seen is that, so there's a thing in C++ called the standard template library. That's where a lot of the collection classes come from and so on. And there's this particular developer who was like, I don't like the binary tree in the STL, I'll write my own better one. And when Microsoft profiled the game, they saw, well, your one is 10 times slower than the standard library. But then it was 20 times slower than if they just used the vector. So obviously that developer had not tested the performance of their replacement. They were just like, STL bad, don't use it. Another developer wrote their own custom min copy function. It sounds like you copies memory anyway. I think you're all familiar with C from the sounds of it, so you probably use min copy. But yeah, their one was slower, so they made it faster by just changing it back. And there was one game that came in and they were wondering it's really hard, we're targeting 60 frames per second, we just can't get there. And when they had a look at it in the profile, they could see, oh, you're rendering everything twice per frame. So they just disabled that, damn, we're way over 60. So measuring what you're doing and checking your assumptions, everything, it's not just guaranteed that people will do this. If you measure and measure carefully, then it's going to help a lot. So, before I go to the next slide, just anyway, the other thing I wanted to mention is just to make sure that your measurements are well targeted as well. Like before I mentioned, maybe statistical distribution of performance can be better than an average, and so on. You need to know what it is that makes the most difference for your product and measure that. And make sure the measurements are repeatable. I've often seen people do measurements, and the way they've set things up, it's just not repeatable. You run it again, you get different results and so on. That's useless. You need to be able to repeat the tests. You need to be able to run it, get exactly the same result, so that what you are comparing are just the changes that you've made. There's not just variation in the experiment. Anyway, how do you measure performance then? How much have you used profiling tools during your course? Anyway, can you put your arm up if you've used a CPU profiler as part of your university work? Okay, 1, 2. Okay, well, hopefully this is useful to you. And part of the reason why I decided to talk about this stuff is because I know in my course, which was a fair while ago now, that there was no talk about this, no talk whatsoever. So I hoped, well, this might be something that's interesting or at least useful. So the first thing that you would want to use is a profiler. So these are tools that will analyze your program and tell you where time is being spent, basically. And I guess we use GPU profilers as well. I'll just focus on CPU profilers for the moment. So there are two main classes of those. So one is a sampling profiler, and those will, you don't need to modify your application or anything like that. It's exactly the same application running. Those will just, say, every millisecond or something like that, sample all the call stacks on all the threads of your program. And when you finish doing the capture, it will show you what percentage of the time the program was in all the different functions in your program. So you could run this and see, okay, 90% of the time when this was running, I was in this function. That's a good spot to start with optimization potentially. There's also instrumenting profilers. So they can require you to do a different build of your program. Like I haven't used it for a fair while, but I think gprof, you had to build a profile command line option. That was an instrumenting profiler, and that will modify the code of your program to record information about what function it is executing and so on. So that can be really good if you want to get really accurate call counts and so on. So you want to know exactly how many times the function was entered or exited and so on. But it can distort the performance of the program. So the code that's added can make the program perform differently. So I would tend to think an instrumenting profiler is good if you want to know exactly what was being executed, and a sampling profiler is good if you want to get a bit more accurate information without modifying the code about where time is actually being spent. But the sampling profiler has the disadvantage that you need to sample for a long enough time on the same thing to make sure statistically you're getting enough samples to get a good indication about what's happening. I'm going to give examples of these tools soon as well, so hopefully that'll make it more concrete. There's also manual instrumentation, which is definitely used a lot in the games industry, where you might, at the start of a function, say, start drawing of shadows or whatever, and that would record some information, and then maybe stacks below that would record other information, like starting to draw or take shadows or whatever. And then afterwards in a tool, you can view that to see, okay, it was in that section for 10% of the frame. I'll show an image of what's called a flame chart for displaying that information, and that can be pretty good for getting an overall indication of where time has been spent in the program as well. All right, so for an example of a sampling profiler, this is the output from the sampling profiler in Microsoft Visual Studio. So you can, if you're building Visual Studio, you can just run any program with this very easily. It's included in any version of Visual Studio, the free version. You can see here that this was in update frame for 41.1% of the time for this particular run of all the tanks. And you can also see the counts for how many times it was in these functions. It was in update frame 765 times. If you look at some of the functions below that, it was only in them once. So maybe before making any decisions about those who want to run for a bit longer and get a bit of a higher call count to make sure that you're getting a bit of a more realistic indication of what the program is doing in those areas. This is another sampling profiler, so this is Intel VTune. So the reason I show this one as well is just because Microsoft's sampling profiler is a generic one. It can tell you where time is being spent, but you could be thinking, I've got the best algorithm, I think this looks optimal to me, I don't know how I could improve this, I want to know why this is slow. Why is this taking, what are the bottlenecks on the CPU when it's running this code? And that's what Intel VTune can tell you, as long as you're using an Intel CPU. When it samples, it doesn't just sample the call stacks, it reads a lot of counters off the CPU, and then afterwards VTune can figure out where was the CPU limited when it was running this code. Was it limited by ALU? Was it limited by L2 cache access? Was it limited by various other things? So that's where a tool like this can be useful. But generally, this is something you would look at after you've exhausted other avenues. So this view maybe isn't so clear, but this is another tool in Visual Studio called Concurrency Analyzer. So this is a sampling profiler as well, and it also is augmented with gathering of some events from Windows. To be able to give us this view, I'll try to point to it a bit. I don't know, I'll try and speak a bit louder, but this is showing green for everywhere that this particular thread is active. And we can click on this at any point and see what was executing on that thread at that time. And what's highlighted here is what this tool can show us is that this thread up here was waiting. And it was only after this thread finished executing this block that this thread was then able to execute. So this can be a really good tool when you've got multi-threaded software for seeing what's causing stalls, how much parallelism am I getting, like where am I seeing idle CPU cores. And something that's not shown in this diagram as well is that it can also, that is really useful for games, is it will show you how active the GPU is as well. So you can see everywhere where the GPU has been idle, the CPU wasn't feeding it enough work and so on. And this is the flame graph for the manual instrumentation that I was mentioning before. So these are basically, each line is a call stack that's had manual instrumentation put into the code, they're recorded out, and then this is a commercial tool, RAG game tools telemetry being used in this case. That the tool will then display all the call stacks were recorded and how long they were active for. So what this lets you just see at a glance is, I'll try to speak loud again, but this is a particular frame of the game, and we can see here, here's this update. Okay, so where's the frame end actually? So this is a frame of the game, and we're doing update frame. Update frame's active the whole time there actually. Then here's the tick. This tick function, and we can see, okay, we're doing script updates here, a world app update there. Then we're doing this present call, and then we're going into draw. So anyway, it gives you a bit of an indication of what the program is actually doing across that frame and what's taking up most of the time. And this can be pretty low overhead. So this is something that you can have running all the time, getting recorded just to get an indication of where this is going. And just one of the last things I'll show, this was for that horizontal and vertical pass thing that I showed before. So maybe it's not so clear, but this is the output from VTune running on that particular program. And so you can see for the horizontal pass, it says 98.7% of the time it's the CPU is just retiring instructions. So VTune's a bit of a complicated tool, it's a bit to learn to know how to read this, but that basically just means it's spending all of its time executing instructions. If you want this to go faster, you just need to make it so there are less instructions, basically. Whereas for the vertical pass, you can see, well, it's 92.7% bound on L3 cache access. And when you can see there, it's 87.3% bound in the back end of the CPU. Once you sort of learn how to read that, it's just super obvious. This is really bound on memory access. If we want to improve this code and make it go faster, we need to improve how we're accessing memory. So that's the sort of insight that Intel VTune can give you. And, sorry, I'll just skip that slide and that one probably. And anyway, so that's what I'm going to talk about. So to summarise, I recommend designing for performance where it's appropriate, where you actually want it as a feature. There is software performance where performance may not be a very high consideration, but if it is, it's got to be considered like anything else you want. You can't just assume that you'll have it at the end. If you want to do a really good job of designing for performance, take into account real hardware systems, the network that you're going to be using, the libraries you're going to be using when doing designs. And measuring performance is critical. If you don't measure, you don't really know what's happening. And like I said before, if you can do these things, then I'd say you're off to quite a good start on doing a good job writing a conscript software. And just some quick recommendations I would have for anyone who sort of wants to try learning more about this sort of thing is, I would recommend trying to use some of these tools if you haven't before, these profilers and so on, just to get an idea of, and it's, if you haven't used one before, it's like really insightful to see, oh, that's what my program is doing, that's where it's spending its time, and so on. I would recommend learning about some more about how CPUs work, especially when it comes to cache and memory access. Learning some of the details of how the collections work that you're using all the time, the data structures in libraries, and knowing some of the relative costs, like I showed on that table of latency numbers every programmer should know as it's got. And that's the end of the presentation. Thank you very much. So, we'll be around for a while to answer any questions that anyone has. And so Richard and I will be here. Isabel and Kira are over there. So if anyone's got any questions about the internship program or wargaming or writing software or anything, just feel free to ask.